What if I told you that in 2010, an iceberg the size of Rhode Island simply vanished from satellite images without explanation, leaving scientists baffled and conspiracy theorists running wild? This isn't some ancient mystery buried in dusty archives or a legend passed down through generations. This happened in our lifetime, captured by our most advanced technology, and yet nobody could explain where 4,000 square kilometers of solid ice had gone. I'm talking about Iceberg B09b, a massive chunk of Antarctic ice that broke away from the Ross Ice Shelf back in 1987. For over 2 decades, this frozen giant drifted to the Southern Ocean like a ghost ship made of ice, tracked by satellites and monitored by researchers worldwide. It was so large that it had its own weather patterns, its own ecosystem, and yes, its own Wikipedia page. But then, in the span of just a few weeks, it disappeared completely. No wreckage, no obvious melting, no massive debris field floating in its wake. One day it was there on every satellite image, a white behemoth clearly visible from space, and the next day it was gone as if it had never existed at all. The scientific community was stumped, oceanographers scrambled to explain what they had witnessed, and the internet exploded with theories ranging from underwater volcanic activity to secret government experiments. Today, we're diving deep into one of the most perplexing environmental mysteries of the modern era. We'll explore the extraordinary life of this wandering iceberg, examine the cutting-edge detective work that scientists use to solve its disappearance, and uncover what this bizarre case reveals about our rapidly changing planet. Because as you'll soon discover, the story of B09b isn't just about one missing chunk of ice. It's a window into the complex, often violent dance between ice and ocean that's reshaping our world in ways most people never imagined. But before we unravel this frozen mystery, let me paint you a picture of just how massive and significant this iceberg really was. When B09b first calved from the Ross Ice Shelf in 1987, it measured roughly 40 kilometers long and 70 kilometers wide. To put that in perspective, imagine the entire city of Los Angeles, but made of solid ice and floating freely in the ocean. This wasn't some ordinary ice cube bobbing in your drink. This was a floating island of fresh water, containing enough ice to supply the entire United States with drinking water for over 2 years. The iceberg didn't just sit still after breaking free from Antarctica. Instead, it embarked on one of the longest journeys ever recorded for a piece of ice. Caught in the circumpolar current that flows around Antarctica like a massive conveyor belt, B09b began a slow but relentless migration that would take it thousands of kilometers from its birthplace. Year after year, satellites tracked its progress as it drifted eastward, carried by currents that had been flowing for millions of years. What made this journey particularly fascinating to scientists was how the iceberg changed as it traveled. Like a sculptor working in reverse, the ocean slowly carved away at its edges, reshaping its contours with each passing storm. The constant motion caused stress fractures to appear across its surface, creating a web of cracks that would eventually play a crucial role in its ultimate fate. Meanwhile, the iceberg's massive bulk created its own microclimate, with temperatures around its edges often several degrees cooler than the surrounding ocean. Marine biologists were particularly excited about B09b because large icebergs like this one essentially function as floating ecosystems. As the ice slowly melted, it released fresh water and nutrients that had been locked away in Antarctic ice for potentially thousands of years. This created unique conditions that attracted specific types of marine life, from microscopic phytoplankton to larger fish, and even seals that would occasionally hitch rides on the iceberg surface. The scientific community had invested significant resources in tracking B09b precisely because it represented a natural laboratory for studying ice dynamics, ocean circulation, and climate change. Research teams from multiple countries collaborated to monitor its progress, using everything from satellite imagery to underwater sensors. The data they collected was invaluable for understanding how icebergs behave in the open ocean and how they contribute to global ocean circulation patterns. But tracking something the size of Rhode Island floating in the vast Southern Ocean isn't as straightforward as you might think. Satellite imagery can be obscured by clouds. Storms can knock monitoring equipment offline, and the remote location means that direct observation is extremely difficult and expensive. Scientists relied primarily on a network of satellites that photographed the same areas of ocean at regular intervals, creating a time-lapse record of the iceberg's journey. For most of its 23-year journey, this system worked perfectly. B09b showed up as a bright white mass in satellite images, easily distinguishable from the darker ocean around it. Researchers could track its position, measure its size, and study how it changed over time. The iceberg became something of a celebrity in the glaciology community, with scientific papers written about its behavior and its role in southern ocean dynamics. Then came 2010 and everything changed. In early spring of that year, satellite operators noticed something unusual in the images coming back from the Southern Ocean. B09b, which had been clearly visible just weeks before, appeared to be fragmenting. Large pieces seemed to be breaking away from the main body, which wasn't entirely surprising given the iceberg's age and the constant stress it had endured during its long journey. What happened next, however, defied all expectations. Instead of creating a debris field of smaller icebergs that could be tracked individually, B09b seemed to be disappearing entirely. Each successive satellite pass showed less and less of the iceberg remaining, until finally, there was nothing visible at all. The ocean where B09b had been floating for over 2 decades was empty. The initial reaction from the scientific community was disbelief. Icebergs of this size don't just vanish overnight. Even when they break apart, the pieces should remain visible for months or even years as they gradually melt. Something extraordinary had happened, but none of the existing models could explain what that might be. Theories began emerging almost immediately. Some researchers suggested that the iceberg had flipped over due to uneven melting, causing the visible white surface to end up underwater, while the darker, previously submerged portion came to the surface. This would make it much harder to spot in satellite imagery, potentially creating the illusion that it had disappeared. Others proposed that B09b had encountered unusually warm water, perhaps from an underwater volcanic vent or a particularly strong current of warm water from the north. This could have accelerated the melting process dramatically, causing the iceberg to disintegrate much faster than normal. The problem with this theory was that oceanographic data from the region didn't show any evidence of unusually warm temperatures during the time period when the iceberg disappeared. A more exotic theory suggested that B09b had encountered the edge of the continental shelf and broken apart catastrophically when it ran aground. The impact of a 4,000 square kilometer iceberg hitting the seafloor would certainly be dramatic enough to cause rapid fragmentation. However, bathymetric maps of the area showed that the ocean was far too deep for this to be a possibility. As weeks turned into months with no sign of B09b or its debris, some researchers began to wonder if there had been a systematic error in the satellite tracking. Perhaps the iceberg had never been where they thought it was, or maybe technical problems had corrupted the imaging data. But cross-referencing with multiple satellite systems and ground-based observations confirmed that the tracking had been accurate. B09b really had been there, and now it really was gone. The mystery deepened when researchers began analyzing oceanographic data from a region where B09b had disappeared. They expected to find evidence of massive amounts of fresh water entering the ocean as the iceberg melted, but the salinity measurements didn't show the dramatic changes they anticipated. It was as if the iceberg had vanished without leaving the chemical fingerprint that rapid melting should have produced. This led to one of the most intriguing theories yet proposed. Some scientists suggested that B09b hadn't melted at all, but had instead been pushed underwater by a combination of wind, current, and its own changing buoyancy. As icebergs age and weather, their density can change in complex ways. If the iceberg had become just slightly denser than the surrounding seawater, it could have sunk below the surface while remaining largely intact. The idea of a submerged iceberg lurking somewhere beneath the waves captured the public imagination, but it raised troubling questions about maritime safety. If something the size of Rhode Island could slip beneath the surface and disappear from all tracking systems, what did that mean for ships navigating the Southern Ocean? The region was already known for its harsh conditions and limited rescue capabilities. The thought of invisible ice mountains drifting through shipping lanes was genuinely terrifying. Meanwhile, climate scientists were grappling with the implications of B09b's disappearance for their broader understanding of ice dynamics. If large icebergs could vanish in ways that existing models couldn't predict, how reliable were their projections about ice loss from Antarctica and Greenland? The stakes couldn't be higher, given that melting ice sheets represent one of the largest potential contributors to sea level rise in the coming decades. The breakthrough in solving the mystery came from an unexpected source. A team of researchers studying ocean currents in the Southern Ocean had deployed a network of underwater sensors designed to measure temperature, salinity, and current strength at various depths. These sensors weren't specifically looking for missing icebergs, but they happened to be operating in the general vicinity where B09B had disappeared. When the team retrieved their data months later, they found something remarkable. The sensors had recorded a series of dramatic changes in water temperature and salinity at depth, occurring at exactly the time when B09B vanished from satellite imagery. The changes were consistent with massive amounts of ice melting rapidly at depth, but not at the surface where satellites could observe it. This discovery led to a revolutionary new understanding of how large icebergs can disappear. The researchers realized that B09B hadn't vanished through any single catastrophic event. Instead, it had undergone what they termed a deep fragmentation cascade, a complex process that had never been observed or documented before. Here's what they believe happened. As B09B aged and weathered during its 23-year journey, it developed an extensive network of internal cracks and fractures. These weren't visible from the surface, but they had weakened the iceberg's internal structure significantly. When the iceberg encountered a particular combination of ocean conditions, likely involving warm water at depth and specific current patterns, these internal weaknesses caused it to fragment from the inside out. Unlike normal iceberg calving, where pieces break off on the edges or surface, this deep fragmentation occurred primarily below the waterline. The visible portion of the iceberg remained largely intact even as the underwater bulk was breaking apart into millions of smaller pieces. These fragments were small enough that they melted quickly in the relatively warm deep water, but the process released so much fresh water that it created localized changes in ocean density and circulation. As the underwater portion of B09B disintegrated, the remaining surface ice became unstable and eventually flipped over or sank completely. This explained why the iceberg seemed to vanish so suddenly from satellite imagery, why there was no visible debris field, and why the oceanographic sensors detected chemical changes at depth but not at the surface. The discovery of deep fragmentation cascades has revolutionized our understanding of iceberg dynamics and has significant implications for climate science. It means that large icebergs can contribute fresh water to the ocean much more rapidly than previously thought possible, in ways that are difficult to observe and track. This has important consequences for models of ocean circulation, which rely on accurate predictions of how and when ice melts. But the story of B09B's disappearance also reveals something troubling about our ability to monitor environmental changes on our planet. Despite having an extensive network of satellites, sensors, and monitoring systems, we could still be completely surprised by natural phenomena. The fact that a Rhode Island-sized piece of ice could vanish without anyone understanding how or why is a humbling reminder of how much we still don't know about the complex systems that govern our planet. The case has also highlighted the importance of interdisciplinary collaboration in solving environmental mysteries. The key breakthrough came not from glaciologists or satellite specialists, but from oceanographers studying something completely different. Their underwater sensors happened to be in the right place at the right time to capture data that no one else was collecting. This serendipitous discovery has led to calls for more comprehensive monitoring of the polar oceans, with sensors designed specifically to detect and track deep fragmentation events. Since the B09B incident, scientists have identified several other cases where large icebergs have disappeared more quickly or completely than expected. These discoveries suggest that deep fragmentation cascades may be more common than anyone realized, which has prompted a major revision of computer models used to predict ice loss and sea level rise. The new models show that under certain conditions, ice sheets could lose mass much more rapidly than previously thought possible. This has obvious implications for coastal communities around the world, but also affects global weather patterns, ocean circulation, and marine ecosystems. The Southern Ocean plays a crucial role in regulating global climate by absorbing carbon dioxide from the atmosphere and distributing heat around the planet. If large amounts of fresh water are entering the ocean more rapidly than expected, it could disrupt these critical processes in unpredictable ways. The mystery of B09b has also sparked new interest in the historical record of iceberg observations. Researchers are now combing through decades of satellite imagery, ship logs, and other records to look for similar disappearances that may have been overlooked or misunderstood at the time. They've already identified several potential cases where large icebergs may have undergone deep fragmentation cascades, suggesting that the phenomenon may have been occurring for years without being recognized. One particularly intriguing discovery involves a massive iceberg that broke away from the Larsen ice shelf in 2002. Like B09b, this iceberg was tracked for several years before disappearing suddenly from satellite imagery. At the time, researchers assumed it had simply melted faster than expected due to warm ocean conditions. But reanalysis of the data using new techniques developed after the B09b investigation suggests that it may have undergone a deep fragmentation cascade similar to what happened to B09b. The implications extend beyond just understanding how icebergs behave. Deep fragmentation cascades may also affect the stability of ice shells themselves. If the process can affect free-floating icebergs, it might also occur in ice shells that are still attached to the Antarctic continent. This could make ice shells more vulnerable to collapse than current models predict, which would accelerate the flow of glacial ice into the ocean and contribute to faster sea level rise. Climate scientists are now working to incorporate deep fragmentation processes into their models of Antarctic ice loss. This is challenging because the phenomenon depends on complex interactions between ice physics, ocean dynamics, and atmospheric conditions. The models must account for how internal stresses develop in aging ice, how ocean currents and temperatures vary at different depths, and how these factors combine to trigger fragmentation events. Early results from these updated models are sobering. They suggest that under rapid warming scenarios, large portions of the Antarctic ice sheet could be lost much more quickly than previously thought. This doesn't mean that catastrophic sea level rise is imminent, but it does mean that the margin for error in our climate projections may be smaller than we hoped. The B09b mystery has also influenced how we think about monitoring other aspects of the climate system. If something as large and obvious as a Rhode Island-sized iceberg can disappear without warning, what other changes might we be missing? This has led to increased investment in monitoring systems that can track multiple types of environmental changes simultaneously, from ice loss to ocean chemistry to atmospheric composition. Perhaps most importantly, the case has reminded us that nature still has the capacity to surprise us, even in an age of advanced technology and sophisticated scientific understanding. The disappearance of B09b wasn't caused by human activity, but revealed gaps in our knowledge that could affect how we respond to climate change in the coming decades. As we continue to grapple with the challenges of a changing climate, the story of B09b serves as both a cautionary tale and a source of hope. It's cautionary because it shows how much we still don't know about the complex systems that govern our planet. But it's also hopeful because it demonstrates the power of scientific curiosity and collaboration to solve even the most perplexing mysteries. The next time you see a news story about melting ice or rising sea levels, remember the curious case of the disappearing iceberg. Remember that behind every statistic and projection are real phenomena occurring in the vast, wild places of our planet. Phenomena that can still surprise and humble us. The story of B09b reminds us that the Earth is far more dynamic and unpredictable than we often assume, and that understanding requires not just advanced technology, but also patience, creativity, and the willingness to admit when we don't have all the answers.